Okay, students, can you hear me?
Yes.
Can, okay, good. Okay, so you can see the document. Can,
Yes.
okay, so okay, today's lesson, let's be something new. Okay, so let's recall back. Okay, recall back slowly. So far we learned about the first two. We did the specific capacity and latent heat, which you already know earlier. Just recall back, and we did some questions, which is slightly more challenging compared to what you have done before in your early studies. So now something lost energy, something gained energy. You must be careful. Check is that is not only MC theta will involve temperature rise. Sometimes melting might happen in between the temperature change. So you need to include ML. So be careful. How to find that? You draw the graph for both substances and check the melting point and boiling. The graph you are supposed to draw is what change in temperature versus the time. Okay, so and check the melting point, boiling point of that substance. If the melting and boiling point of the substance is in between the temperature change, then you should know the change phase had already occurred. So you have to include ML. Okay, so today's lesson is the first 4 hours. We're going to focus to internal energy. So we learn about specific capacity. We learn about how the particles are, what the bonding looks like. And we talk about joule per kg per kilogram for MCT, what do you call specific capacity. Okay, so today's lesson, I think before we go to internal energy, we haven't done evaporation, right? So we start with evaporation. Okay, go to the slide. Okay, so today we're going to talk about evaporation. This also you learned before, right? Evaporation. Okay, evaporation, same stuff you want to recall back. Evaporation is what? It's a phenomenon that occurs at the surface of the liquid and involves change of state from liquid to gas at any temperature. Okay, normally evaporation will be compared with what? Boiling, right? Evaporation and boiling. Anyone can tell one similarity between evaporation and boiling? Okay.
Both is conversion of liquid to gas.
So it's a liquid gas. So conversion from liquid to gas. So that's the only one similarity, I think. There are another similarities, but this is the most one which make them to compare. Okay. Okay. So now, two difference between evaporation and boiling.
Evaporation occurs at any temperature, but boiling only occurs at the boiling point.
At the boiling point, yeah. So, yeah. So it happens at any temperature. Boiling happens only at the boiling point. Evaporation occurs only at the surface. Boiling happens in entire liquid. Okay. Then evaporation affected by the wind blow. Boiling not really affected by the wind blow. Evaporation and boiling both affected by atmospheric pressure. Is evaporation affected by atmospheric pressure? Higher the atmospheric pressure, rate of evaporation become higher or lower, or no change?
No change.
No change. Evaporation, atmospheric pressure. Let's say you have a liquid, okay, liquid full of molecule, okay. The energetic particle want to come out from the liquid phase to the gas, but the pressure here on top, the atmospheric pressure is very high. It means very high pressure means what? Here itself, the particles are crowded. They are more crowded. How can this water molecule can absorb into the air? So they have difficulty to get into a gas state. So what happened? When atmospheric pressure is very high, the evaporation become low.
Okay.
Difficult to evaporate. How about boiling? Is it boiling affected by atmospheric pressure?
Yes.
The same story, right? The same story. Boiling also difficult to happen. And of course, I believe some of you have learned when atmospheric pressure rises, the boiling point of water, which is 100 degrees Celsius, will rise little higher, right? Maybe 101 degrees Celsius, so on. So atmospheric pressure, I think, is a similarity. Okay, recall back why when evaporation takes place, the liquid cools. Okay, another one main differences is evaporation causes a cooling effect. Okay, after the evaporation happens, but boiling, is it give a cooling effect? No, boiling does not give a cooling effect. Okay, do evaporation need external energy for the evaporation? Boiling need external energy. Boiling need external energy. You need to supply external energy for boiling to happen. But evaporation, you need energy for evaporation to occur, but the energy is not externally supplied. Okay, the energy is taken within the particle. That means internal energy has been used, not external energy. Okay, for evaporation. Okay, so let's move on. Okay, now the question they're going to ask in exam is why evaporation causes the temperature to fall. You have to tell the story. Okay, why temperature falls. So this is the explanation which I believe most of you know before. Why the temperature falls? Because in a liquid, the molecule collide randomly each other, exchanging momentum. The keyword is the result of wide distribution of kinetic energy from very small to very large energy. Yeah. So you must tell that the particle has a range of kinetic energy. Particle will have a range of kinetic energy at a particular temperature. Okay. So range of kinetic energy. At the surface, the liquid, more energetic, fast-moving molecules can easily escape. So this is one mark. This is the main point. Because evaporation means it's a process where the most energetic particle escape from the liquid. So at the surface, the most energetic particle will escape from the surface. Then what happened? The second point, the slower molecules remains. Okay, so still not mark, no mark for this. Then the last line, as kinetic energy are lost continuously, the average kinetic energy of the remaining molecule decreases. Yeah, of course, this is same like your class law. A class, we have good students, average, mediocre, and weak one. But let's say the good students leave the class to another class. What happened to the average mark of the class? Will drop. So same thing happens here for kinetic energy. The average kinetic energy of the remaining molecule decreases. Okay. Then the last point you have to tell. Therefore, the temperature falls. How do you know? Kinetic energy drop means temperature falls. The topic you learned earlier. 3/2 kT is equals to average kinetic energy of the particle. Mean kinetic energy of the particle. Don't forget to tell mean. Average kinetic energy of the particle. So this is the proof that when the mean kinetic energy drops, the temperature drops. This is one mark. So 3 marks, you must say the particle has a range of kinetic energy at one particular temperature. At the surface, the most energetic escape. Then the average kinetic energy of the remaining molecule decreases, therefore temperature falls. Okay. This is the reason you should recall. Okay, I believe you learned this reasoning earlier, but now you know a little extra. The temperature determines the kinetic energy. Okay, now you know the formula. 3/2 kT equals to. Okay, any questions from here, guys? So this is a fact to remember. Okay, so rate of evaporation. How do you make evaporation faster? Okay, so first, let's say you have a cup of coffee. How do you make evaporate faster? Okay, so the area of exposure, because I tell you about coffee, so I talk about the second one first. The area of exposure. Greater the area of exposure, greater the evaporation. Okay, you can see some old people when they drink coffee, they normally pour the coffee on a plate, make the coffee exposed to a bigger area, so the evaporation rate of evaporation become faster. Okay, so area affects exposure. Area of exposure affects the evaporation. Definitely temperature of liquid. More higher the temperature, more faster the rate of evaporation. Humidity surrounding the air. High humidity, difficult to evaporate. Okay, too much of water contained gas. Wind, more faster, the greater the wind, greater the evaporation. Pressure, low the atmospheric pressure, greater the evaporation. And of course, the last one is the nature of the liquid, which is very low profile, nature of the liquid. Alcohol, very volatile, easily can evaporate. So it depends on the nature of the liquid compared to water. Okay. So these factors, which affects boiling? Which affects boiling in these factors? Similar as evaporation. Anyone?
Temperature, pressure, and nature.
Yeah. The temperature of the liquid. Yeah, okay. Temperature of the liquid. Anything else?
Pressure.
But temperature, okay. Then pressure, yes, pressure. Okay. And we can say nature of the liquid also. Low melting, boiling point, easy to boil. Okay.
Yes.
Yeah. Any questions? No questions, Okay. Okay, these questions all I skip. This is about MC, theta, and ML. Straight we go to today's lesson. These all are questions you can go through. The PowerPoint. Okay, today's lesson is about internal energy. Okay. So do you heard about internal energy or early studies?
Technically.
No. Technically, yes. You learn about internal energy. Do you? No. Okay. Let me recall back. Solid, liquid, gas, which has the greatest internal energy?
Gas.
Gas has the greatest internal energy. Why? It's moving a lot. Okay, what is meant by internal energy? Internal energy is the energy you can't observe from outside. Okay, now you are sitting on the chair, so you can see the table. The table particle inside for you looks like it's not moving. Okay, and but in reality, the particles inside the table has some energy. The table particle, we know that microscopic level is, so they have some sort of kinetic energy. Okay, and because each particle has an intermolecular force, so they do have some sort of potential energy. Okay, so what is internal energy meant by for a substance is the sum of what? The sum of kinetic energy and potential energy possessed by all the molecules due to moving randomly within the system. That's called internal energy, U. So to be simplified, this equation, something missing. The internal energy is the sum. Put the summation sign. Sum of kinetic energy and the sum of potential energy possessed by all the particles in the substance due to random movement. Okay, you must say due to random movement. Okay, this is internal energy. Okay, this is internal energy. Okay, so just now I asked solid, liquid, gas, which has the greatest internal energy? Just now some of you told me it's a gas. That's good. It's a gas. Why gas? Because gas has the greatest kinetic energy compared to solid, liquid, and gas. Okay, so solid, liquid, gas, which has the greatest EK? Of course, gas. You know that, no problem, because it's moving a lot. Okay, now potential energy. Which has the greatest potential energy? Solid, liquid, gas. Anyone? What do you think? Which has the greatest potential energy? Solid, the atom are very close by.
Also gas?
Yeah?
Also
yes, good. Gas. Gas, again, is the winner here. It has the greatest potential energy. Okay? So how do we know it has the greatest potential energy? Last time we thought that intermolecular force. Yes, the intermolecular force, like Earth. You compare with Earth. Earth, you are standing here now in your house. Okay, you are in your room now. Let's say you climb upstairs, go to higher places. at the room is the position A, and then later you go to the climb stairs, you go to the higher position B. So tell me, the new knowledge you learn under gravitation, potential at A greater or potential at B greater? Potential energy. I mean, you have a greater potential energy at A or greater potential energy at B?
B.
At
B.
B. At potential energy B is greater than potential energy at A, right?
Yes.
Yes, because it's less negative. Eh? Maybe at potential energy at the surface you got negative 80, but when you go higher, maybe it's negative 70. This negative 70 is greater potential energy than negative 80. Okay. The same thing happens here for the particle. The particle close by, they are attracted to each other, like Earth. Earth is attractive. More stronger the intermolecular force, more stronger the intermolecular force, the potential energy is highly negative. Highly negative. Remember, it's highly negative. So we said low potential energy. Highly negative means low potential energy. Okay. So when it comes to case of solid, liquid, gas, solid has the greatest highly negative potential energy. Okay. Liquid has less potential and negative energy. Gas, okay, gas is a trap. Gas got how many types of gas we have? We got real gas. Another one gas is what? Ideal gas. Okay. Ideal gas potential energy is zero. This is what they're going to test a lot. The potential energy for ideal gas is what? Zero. For real gas, the potential energy is close to zero. That means it has some negative value, maybe -5. It has a very low negative value. It's not zero for real gas. Ideal gas, potential energy is zero. Why? Anyone? Why potential energy for ideal gas is zero?
Intermolecular forces are negligible.
Very good. We can say it, you can't say it negligible. Yeah. Ideal gas, what is it?
No
No
inter-
intermolecular force. For sure, you can say there is no intermolecular force. So therefore, no intermolecular force, absence of intermolecular force, potential energy is zero. Okay. So because gas has the greatest EK and EP, so gas has the highest internal energy. Has the highest internal energy. Okay. Okay. So about internal energy, an increase in internal energy can mean an increase in EK or increase in EP. Okay. If they say a substance increase its internal energy means you should know either it increasing the EK or increasing in EP. Okay. So how do you can rise internal energy of a substance? How do you can rise internal energy of the substance? Either you increase the EK or increase the EP. Okay. How do you increase the EP? EK. How do you increase the EK? You already know this earlier one. You want to increase the EK, increase the dependent to absolute temperature, right? So increase the temperature, EK rises. Yes. So rise temperature, EK will rise. Therefore, internal energy rises. Okay. So that is how to increase EK. So we can conclude that EK proportional to what? Temperature. Rise the temperature, kinetic energy rises. So we quite stabilized this idea already. Kinetic energy proportional to temperature. So temperature rise, EK rises. Okay, now how do you rise potential energy? Potential energy, what do you have to do? Potential energy, you want to energy means the potential energy means less negative. Okay, less negative. So how do you do that? Increase the separation of the particles. Okay, greater the separation, or in other words, the best is reduce the intermolecular force. Try to reduce the intermolecular force. How do you can reduce the intermolecular force? By increasing the spacing or decrease the spacing? By increasing the spacing, right? So potential, we can say it is directly proportional to spacing. Greater the spacing of the particles, greater the potential energy. Okay, important. Increase the spacing, increase the potential energy. Solid liquid gas like gas has a greater spacing, so greater potential energy. Okay. So this is the two ways law. Okay. Now you know at the top. Let me draw a graph. Okay. You melt. I think chemistry you use naphthalene, right? Naphthalene too. Do you do that experiment? Melting it,
Yeah.
melting it. Just okay. So how the graph looks like? Go up, flat, go up, right?
Yes.
Okay. At 1, 2, 3. At 1, yeah, internal energy rise or not? At 1,
Yes.
internal energy rises. How internal energy state rises? EK rises or EP rises?
EK.
At 1, EK rises. EK rises, therefore internal energy rises. Why EK rises? The reason you have to tell. You say because temperature rises, therefore EK rises, therefore internal energy rises. Okay. Don't straight away say EK rises, therefore internal energy rises. You must say why EK rises. You have to say temperature. Huh? Temperature rises, therefore EK rises, therefore internal energy. Okay, 3 also the same thing. 3 also the EK rises. Okay, now we focus to 2. 2, internal energy rises.
Yes.
Why internal energy rises in 2?
The potential energy rises.
Yeah,
Because first, the energy is used to overcome the intermolecular forces.
okay, the best answer you said. The potential energy rises because the spacing between the particle increase. Don't say spacing of the particle. The potential energy rises because the intermolecular force get weaker. Okay, potential rises because the intermolecular force get weaker. So at 2 also internal energy rises, but rises by increasing a different energy EP. So whenever phase changing, EP changing. Whenever temperature rise, EK changing. So both contribute to internal energy. Okay. Okay. So now I need to talk about some exception now. Yeah. Okay, let me get this. Yes. So talking about EP. EP found to be proportional to what? Spacing. I told you spacing, right? Spacing, right? But actually EP increase when intermolecular force, molecular force
Decrease.
decreases. This the actual fact. But what we know normally, when intermolecular force decreases, normally, spacing will spacing will rise. Correct? Spacing will rise for all the substance. For all this, that's why because EP rises because intermolecular force get weaker, spacing increases. So therefore, we conclude EP rises means spacing rises means EP rises. That's why we conclude the above relation. But is it all the substance when intermolecular force get weaker, spacing rises? Is there any substance intermolecular force get weaker but spacing decreases? Do you have any substance? Do you have any substance? Any substance when intermolecular force get weaker, spacing decreases? Anyone?
Ions.
Yeah? Anyone? It's a well-known liquid for you.
Ice water.
Water, yes, good. Water, H2O. Okay, water. Okay, water. You can see there, right? Solid, liquid. Focus about solid liquid and gas lah. Solid liquid. Okay, solid liquid. Solid. Your ice cube. Okay, your ice cube denser, or when it melted, become water denser. Ice cube denser or water denser?
Water.
Water is more denser. Okay, so that means spacing between the water, the atomic is greater, right? But water has a low internal energy. Internal energy is low, but spacing decreases. For the water, the spacing is decreases. That's why it become a tensor. So The concept above, EP proportional to spacing, not applicable for what? Not applicable for H2O. Not applicable for H2O. Okay. So when you explain H2O from solid to liquid, don't say potential energy. Potential energy is still getting lower or higher. Come on, anyone. Solid to liquid. Potential energy get lower or higher. Solid to liquid. Normally, solid to liquid spacing increases, intermolecular force get weaker. So we say potential energy get smaller. Correct. For water, solid to liquid, liquid get denser. Liquid get denser. The intermolecular the spacing gets smaller. So therefore, is it potential energy gets smaller or bigger?
Potential energy still
Get smaller, right?
Okay.
Still get greater, right?
Greater. It's just the structure.
Why? So in this case, can you say the spacing as a reasoning? You don't. Spacing is just for us to see the proportionality to the potential, but the actual reason is what?
Structure.
The intermolecular force. Whenever you talk about potential energy, spacing is like a reference for all the substance. But when you explain, you say the potential energy increases because the intermolecular force get weaker. That's what you should have to tell. Okay. So the purpose of I'm explaining this is actually you always can imagine when spacing increases, intermolecular force get weaker. Okay. But when you explain potential energy, what happened? So you say potential energy get weaker because don't talk about spacing. You just straight away say intermolecular force get weaker. The potential energy get weaker. Get greater. What I'm saying. Potential energy increases because the intermolecular force get weaker. Okay. The idea. So be careful with the water. But conclusion is any substance going from solid, liquid, gas. Okay. The EP is move from here to here. EP is definitely increasing. Okay. Why? Why? Intermolecular force. Intermolecular force get weaker. Is the most best way of explaining. And of course, EK also rises. EK rises because, of course, why rises? Because proportional to temperature. So temperature rises, EK rises. Okay. Any questions, guys, from here? Can
Teacher, why is the EP of real gas close to zero?
EP of real gas. Why EP of real gas close to zero? EP of real gas, it's not zero. It's not zero. It has a value. Okay, it has a value. The value very little negative, very little small negative. Okay, because it still have some intermolecular force. As long as you have an intermolecular force, you definitely have EP. But intermolecular force for real gas is very little. So the EP of real gas is like very close to zero. That means not big magnitude. That's what I meant. Okay, get the idea, Shike?
Then the EP of solid, is it more negative than real gas or less negative than real gas?
Solid, liquid, gas. Solid has a high intermolecular force, right?
Yes, so it's more negative, is it?
Yeah, it's more negative. More negative. Liquid less negative. Gas is like real gas zero. Yeah.
Oh, okay.
Okay. So we say EP is rising because it's become less negative. Same story as the planet. Okay. The potential energy is highly negative. When go further, become less negative, become zero. When you go higher, the EP, the potential energy is actually rising. In other words, get less negative. Okay. Same thing for the particle. Okay. Any questions? Any other questions? No questions, Okay. So yeah, this is the core of internal energy. Okay. What is internal energy means? the sum of kinetic energy and sum of potential energy possessed by all the particles in a substance due to random motion. Don't forget the word due to random motion. Sometimes random motion given mark, 1 mark. Okay, so better write due to random movement. Okay, so this is internal energy. Okay, so I think I already tell what are the important things. Okay, next, final part of the topic is thermodynamic. Okay, okay, let me introduce you a little. We have time. Okay, this is the last part of your topic. Okay, and this is the most something new you learn, and something can give you trouble. Can be difficult to not to say difficult to understand. Something new you learn. Okay, for engineers want to build an engine of a car. Okay, to make the engine more efficient, the law they would be in their mind is thermodynamic laws. Yes, thermodynamic laws. Okay, we have 2 thermodynamic laws. Okay, first law and second law, but in your syllabus only first law. Okay, thermodynamics. Thermo is what? Thermo is like heat, right? Heat. Thermo, temperature change, heat. When heat is applied to the system, dynamic what? It influences the movement of the particle. Okay, thermodynamic. How the fluid particles like liquid and the gas particles influenced by the heat. What law governs their movement? It's called thermodynamic law. The law of thermodynamics. Okay. So yeah. So we're going to talk about fluid law, liquid, fluid. The movement of the particles is of course affected by the heat. But what do we have any law to show how they're going to move, how the movement going to look like? Okay. So the first law from the scientists, they say first thermodynamic law says that the change in the internal energy of a closed system is equal to the heat enters the system and work done on the system. Okay. What is meant by this? Okay, let me put in an easy way. Okay, put in an easy way. Okay, just go back here. Okay, let's say you have a closed system. Thermodynamic works for closed system. You have a piston here. You have gas inside. Okay. Okay. My question is, how do you make this gas hotter? How do you can make the gas hotter? By heating, right? By heating, right? Okay. So I said, how do you make the gas hotter? Why I say gas hotter? When the gas become hotter, what happened to the internal energy? Increase or decrease?
Increase.
Increase, goes up. So question is, how do you change the internal energy of the gas? Change the internal energy of the gas. How you can change the internal energy of the gas? You know internal energy is what? Ek plus Ep. The sum of Ek plus Ep. How do you make the particle to move have greater kinetic energy? How do you make the particle to have a greater potential energy? And so on. So how do you make, basically how to make hotter, right? Because Ek proportional to temperature. So by heating it, so that's the first law. To change internal energy of the gas, changes of U is equals to by heating. Okay, by heating the substance. Okay, by supplying energy to the substance, plus another one way. If you don't want to heat, let's say you never heat. Another way, how you can make the gas hotter? By compressing it or by expanding it.
Compression.
By compressing or by expanding, the gas become hotter.
Um,
Compressing, yeah? Is it compressing or expanding? Compressing, right?
yes.
Like a bicycle pump, bicycle pump. You go and bicycle, you pump, compress the air inside the pump. After that, you go and touch at the bottom, it become hot. When gas is compressed, it become hot. Correct? The fact you know that practically. So when the gas is compressed, the internal energy rises or decreases. When you compress the gas, the internal energy rises or decreases. Anyone? Increases, right? Compress the gas become hot.
Yes.
Gas become hot means kinetic energy has been raised. That means internal energy has been raised. So what is another way? What is another way to change the internal energy? One is by heating, plus you do work on the system. Compressing is actually work. What is work? Force times distance travel. Force times distance. Force, you apply a force times distance travel. Okay, a distance travel. You apply a force. So work is force times distance. Okay. So force is what? Pressure times area times the distance you travel, area cross-sectional area. Then this formula tend to become what? Pressure times A times D is what? Changes in volume, work. Okay, P changes in volume. So this is where the first law has been discovered. Okay, so finally they said what? You want to change internal energy of a system of a gas, is you can do that by supplying energy to the system. Okay, Q, you put the symbol of Q, plus work done on the system. This is the formula. This is first law. Okay, first law of thermodynamics. This is based on conservation of energy. Energy is conserved. Okay. So yeah, this law is exactly same as your biological system. I can analog to your body also. How to analog like this? Like let's say you are here. Okay, the changes of U equals to Q plus W also can works for you. Biologically we can adapt. Okay, you see, how do you increase your body internal energy? Body internal energy means more fat. Okay, more fat. You store energy lah. How do you store energy in your body? Become more fat. How do you store energy in your body?
Nothing.
What affects the amount of energy stored in your body? It depends to the amount of this like your this your internal energy amount of food intake. Food intake. Your Q is like the food intake lah. Food intake means energy. What energy supplied to your body? And next is what? It also depends to the amount of work you do, right? What of work you do, right? You do more work. What happened to the internal energy? Internal energy reduces or increases. You do more work. The internal energy will reduces, become more negative lah. So same system. You have a piston. You have a gas. You want to rise the internal energy. The change in internal energy is always Q plus W. Okay. So let's say I am asking you. You heat a gas. You heat. Okay. You heat a gas with the energy supplied 50 joule. Okay. And the gas is expand. Okay. The piston move up, expand, and the work done by using P changes in volume is found to be, let's say, 20 joule. The gas expand. Okay. What is the rise in internal energy?
30.
That's good. 30. The heat is 50 joule. 50 joule trying to rise the internal energy. Like you are eating 50 joule. So internal energy has chances to rise 50. Okay. But the gas expand. The gas expand means equal to the amount of work you do. You are, after you eat, you do lots of work. You run and you bring something on the ladder or something. So you do work. You are burning your fat. So when the gas expand, the work done is considered as negative 20. Negative 20. Negative means what is why negative? Why expand? We label it as negative energy because give a negative effect to the internal energy. Give a negative effect to the rise in internal energy. So work expand means we put negative. Compressed means we put positive. Okay. When gas compressed, it increase the internal energy. The gas become hot. Okay. Okay. So yeah, this is how it works. Okay. So for this gas, you heated 50 joule and it expand for 20 joule. Okay, go up by 20. Work done is 20 joule. So the internal energy rise by 50 minus 20. The work is negative 20. Okay. Any good idea? Let's say I put another. Okay, this never happened in the nature, but I just show you. Okay, okay, another piston again. Okay, I heat it. I heat with 50 joule, but this never happened naturally. At the same time, let's say you compress the gas. You yourself go and compress the gas. You compress the gas, and you did work. Work done by you is 20 joule. What is the rise in internal energy? So, internal energy, according to the first law, the amount of heat energy supplied to the system plus work done on the system. On the system, you must say it on the system, is supplied to the system. Okay. So, Q is, in this case, how much? Positive or negative? Heated one. So, it's positive 50 plus work done, positive or positive 20 or negative 20? Compressed. Compressed, positive 20. Okay. So the change in internal energy is how much? Positive 70 joules. Okay, this is the change in internal energy. Okay, the internal energy has been increased by 70 joules. So this never happened. We heated at the same time we compress it. Okay. So we don't want the engine to move, we compress it. So the internal energy of the gas will rise a lot. I mean the gas become very hot. Okay, and this rises a lot. So energy rises, of course, the temperature. Temperature rises, that means the kinetic energy rises, so internal energy rises. Okay. So we go back to the. Now I hope you understand the law. Okay. What the law said? First law of thermodynamics states that the change in the internal energy of a closed system. Sorry, I forgot the word. Closed system. This only works if it's a closed system. Open system, this doesn't work because it interacts with the outer surface, so it doesn't work. It have to be a closed system. Like combustion engine internal parts, the room where the air has been compressed, and it's a closed system. It works. First law of works. So the rise in change in internal energy in a closed system is equal to the heat enters the system and work done on the system. Don't forget the word on. Okay, if on you put it as by, everything going to be the other way around. Should be on. On means compressed, we take it as positive. Compressed, we take it as positive. Expand, we take it as negative book. Okay, if you put on the system. Some books, instead of on, they put by the system. Okay, by the system. If they put by the system, compressed will be negative, expand will be positive. The other way around. So in our syllabus, the way I'm going to focus you on the system. On the system means compress, work is positive, expand, work is negative. It's clear, So the word must be always on the system. Okay. Okay, this law based on what conservation? This law based on conservation of energy. Energy is conserved. I just now I told you like a biologically. You eat food, you eat 50 joule of energy of food, okay, and you do work of 20 joule. So what the body will do? You supply the body with 50 joule. It means your 50 joule is your Q, your energy you supply to the system. But you only did 20 joule, W. W only did 20 joule, maybe negative 20 joule because you did work. So what the body will do? The 30 joule is going to store as fat, as a store energy. Okay, changes of U equals to Q plus W. So Q is you eat food of 50 joule, but you did work, so negative 20 joule. So the balance 30 joule have to be your change in internal energy. You store energy. Your body stores energy as a fat. Okay, so this reaction not only happens in our biological body, also it happens in the gas. Gas also does the same thing. Okay, you apply heat. If the gas never do work, the gas store it as the internal energy. You know, I want to ask you a question. For as a human, for our for human for us, okay, we always think for our benefit. You know, tell me, human is it favoring to our human what do you call our need? Do we want the internal energy to rise, or do we don't want the internal energy to rise? Is it good or bad for us, human? Anyone? You have a gas system, you heat the gas, and the gas convert the energy you supplied as an internal energy. Is it good or bad for human?
Bad.
It's bad. Like for car engine, you go to the car engine. I'm talking about good or bad is in terms of car engine. Okay, our transportation. Okay, our transportation. Okay, you have a car. Okay, car. So there is an engine here. Okay, of course there is petrol inside. Okay, you start the car. What happened? The system is actually a piston. You have so of course, sorry, the system. You have the piston here. Okay, piston, and at the top, there is fuel is already inside. You burn the fuel. Okay, energy has been supplied. You supply the energy by pouring the petrol inside the combustion region. Then what happened? Explosion happened. Q, the piston goes down. The gas inside here, the whatever energy supplied is stored as internal energy. Is it favoring us?
No.
No. The whatever Q you supplied, what our intention? Want to change to what?
To useful work.
Work. You want the Q to convert to work, not the Q convert to internal energy. Okay. So let's say changes of U equals to Q plus W. Okay. Just now earlier I told you there is a piston, a system. Q applied was 50 joule, and the expansion done is 20 joule. Okay, expand the gas expand. The work done by the gas is 20 joule. Okay, but heat supplied is 50 joule. Okay, now I'm asking you one question. What is the efficiency of this engine? Anyone? Can give a try. Wrong, never mind. Just think first. How human going to rate the efficiency of this engine?
40%.
Yeah. Again,
40%.
it's 40%. So how you get 40%? Because efficiency is what? Output energy or output power, output energy. I put here energy. Output energy over the input energy. So output energy for us is which? The work expansion, the work done. Is the output energy. The input energy is what? Your Q. This is efficiency for us. So work in this case was 20 joule, but input heat is 50. So it's yield to 40%. So the efficiency of the engine is 40%. So is it good or bad? So 30% turn to become internal energy. So we don't want it to rise internal energy. Internal energy causes lots of problem for the engine. What type of problem we give? If internal energy rise, what rises? Means what is the indication rises? The temperature going to rise, What happened? The piston, the engine going to overheat, and when the engine get overheat, you can see like every time daily highways, when the engine get overheated, what happened? The piston, the what do you call, the cylinder all going to the casket on top going to leak. Okay, the water and the what do you call, the petrol going to mix up, so you're going to spoil the engine. Okay, sometimes even the engine, the steel bar, now the engine, some engines are made of aluminium. It's not heat resistance. Very high temperature, even the aluminium going to bend. Okay, more friction, so the engine going to end up catastrophic failure. Okay, so changes of U is bad for in engineering. Okay, so what technology is now doing? What the scientists now doing? The engineers, the automobile engineers trying to do? They're trying to convert Q more to what? More to do work, not to change to internal energy. That's where all the technology comes in. So your VVTI, your VTech, all type of technology, the fancy names they are putting. Everything, the core idea is to have a better, more efficient engine. Okay, I believe maybe some of you are interested in cars, automobile maybe. What is the efficiency of the car engine currently? Anyone? The combustion engine. What is the efficiency of your car engine now? Combustion engine. Anyone can search from the net. What is the
30 to
efficiency?
35%.
How many percent?
30 to 35%.
30 to 35%. 30 to 35%.
Gasoline engine.
Gasoline engine. You check from the net.
Yes.
So 30 to 35% means what? I think about 65% all convert to internal energy, rising the temperature. Guys, if you can build a combustion engine which efficiency of 60%, or you can create a system which has an efficiency of 60%, you are already a millionaire. But we already have one system already. What system? Electric cars. Electric cars using motor, electricity cars. I think efficiency is higher. Okay, again, please check from the net. What is the efficiency of the electric motor, electric cars engine? Please check. Tell me what is the how many percent?
EV motor, I guess 85 to 90 or 77, like that.
Check from the net how much they give. Show you.
77% of the electrical energy from the grid to power at the wheels.
77%.
It's about that.
So around 77%. New technology, electric cars. Okay, is the best technology. I think combustion engine 30 to 35%. I think in the future, nearly future, I don't think so. We're going to use combustion engine transfer to electrical cars, which has a very good efficiency. Very good efficiency. You can imagine what you pour fuel today, and maybe your parents, let's say, they drive car for 1 week. Actually, in reality, the fuel can be used for 3 weeks. Because if efficiency is 100%. Okay, if you use electric car, I think it's 2 times more efficient than the combustion engine. Okay, so all this calculation has been related to first law of thermodynamics. Hey class, so I think I already informed you a lot. Okay, so I stop here. Time's up. So we'll continue next class. 10 o'clock. Okay.
Wait,
Sorry.
Our
Yeah.
class is until 10.
Oh yeah. 8 to 10 right today. sorry. I'm thinking of 8 to 9 and 10 to 11. Okay, good. So guys, any part you don't understand? Okay.
Teacher, why when I compress the air, the work done is positive again? Because when when I compress the air, the potential energy increases, but because the distance between the particle doesn't it decrease? Doesn't the potential energy decreases?
Oh, okay. Okay, going to that first law. So internal energy is EK plus EP, yeah? EP. EP for a gas when the intermolecular force EP is dropping. Okay. So internal energy. Oh, okay, yeah. Yeah, the potential energy of the gas decreases, but the kinetic energy will rise. Causes the overall effect is changes of U rising. But it's governed by the first law. Changes of U equals to Q plus W. Okay. Because W, of course, try to decrease the spacing. So EP like dropping. But heat, the heat, you apply heat, heat going to rise the kinetic energy, right? Heat going to rise the kinetic energy. Right? So, but overall, we check lah. Q was 50 means, but W is only 20. So the winner is the Q lah finally. So therefore, we found the changes of U if positive means, we know one go down, PP go down, EK goes up. So overall, the winner is U found to be positive. That means overall, we can visualize EK increases greater than the EP drop. Okay.
Okay.
And I can get idea because EK also affect the U. Okay. So let's we go back. So to the slide. Okay, so the first law of thermodynamics states that, again, recall back the law and try to understand by heart because used by engineers for fluid. The first law of thermodynamics states that the change in internal energy, you want to rise the temperature of fluid, liquid or gas, you need to do heat need to be supplied to the system or work done on the system. You compress it or expand it, you can change the internal energy of the gas. Okay, if internal energy rises means most probably indication that the gas temperature is rising. Okay, and the internal energy decreases means the temperature is dropping. Okay. Next, I think I already explained this to you. Change of U equals to Q plus W. Q, the higher the temperature, the lower the high. Okay, positive when heat is transferred to the system. Positive when heat is transferred to the system when you heat it. Negative and transferred from the system. From you transferred, remove from the system. That means you cool it. You heat. W is Q is positive. When you cool the system, Q is negative. Okay, heat Q is positive. Give a positive effect to the internal energy. Cool, Q is negative. Give a negative effect to the internal energy. Okay, next work positive when work done on the system. What I told you, when you compress, compress, work is positive. Expand, work is negative. Okay. Okay, one example. I'll give you 1 minute. Look at the question, look at the solution. Okay, guys, so I hope you understand the working and the question. A fixed mass of idle gas absorb 2000 joule of heat. So this is about your Q. Positive 2000 or negative 2000 in your mind. Because the heat has been absorbed by the gas, like you are eating the food, right? So Q is positive or negative? Positive 2000 joule. Okay, give a positive effect to the internal energy. Okay, and does 500 joule of work to expanding work is positive or negative? Expand, work is negative. So it's negative 500 joule in your mind. When you fit it into the formula, work must be negative. Because why negative? You try to decrease the internal energy of the system. Okay, yes, correct. So therefore, first question, what is work done? What is work done? 500 joule. How much does the volume change? P changes in P changes of V is your work done for your gas. Okay, but I tell you more further. In reality, pressure versus volume. The pressure versus volume, if it's constant like this, in reality, the area under the graph, area is the work done. Okay. So P changes in volume only can be used when what constant? Anyone? P changes in volume means what we are assuming? The pressure is constant. Pressure constant, you can choose P changes in volume. If pressure changes in volume, a curve, what is work done? Can you use P changes in volume? You have to use supposed to be your integration format. You know, integration last time you learned in maths. The area and the graph, what's the formula? You do integration, right? Area and the graph. PV, how do you put into an integration format? Integration of anyone? P versus V, area and the graph. Can you put integration format? P dV, right? Integration of P dV. That's your work, correct? Now this is the actual format of writing the work. Work is the integration of P dV. That's your area and the graph. This is your work done. Okay. If you go further studies, maybe in A level, maybe in universities, let's say you take physics or engineering, for a gas of expansion, they ask you to write work. They normally won't write P changes in volume. Okay. They will write integration of P dV. The area and the graph of P versus V is the work done. Okay. But in your syllabus, 90% of the question will be P changes in V because the pressure is constant. So if pressure constant, the area is like a square. So it's P changes in V, P times changes in volume. Okay. So there is also a question with a curve going down. If you have a question which is going down, then how do you find the work done? Don't use P changes in volume. So you state the work done is the area under the graph of P versus V. How do you find the area under graph? Count the boxes. Count the number of boxes. TDS, but it happens. Okay, in your past year. Okay, so this something came up from my mind for you to understand. So work done is P changes in V, assuming the pressure is constant. Then changes in volume, you get this answer. Okay. So in exam, they never tell the graph is a curve or a straight line. They just tell work done is 500 joule. We are assuming pressure is constant. So P changes in volume and we get that. Okay. So the change in volume have to be 0.025 meter cube. Okay, any questions so far about the PV? Anyone can understand? Can
So that means you need to do integration.
Yeah, integration your maths knowledge Last time do Y versus X. You want to find the area and the graph Y versus X. How do you put the integration format? The area. You put integration of Y dx, right? Okay, guys. Anyone without additional maths in this class? If you never take additional maths from 5, I don't think so you learn this. But now in maths, do you already learn integration? You're taking maths. Are you already learn integration in your maths?
In A-level maths, yes.
Yes, you already learned integration already. Then you should know what. The area is integration of Y dx. So, but integration is to find area of any type of graph. If y-axis is your A, X-axis is B. You want to find the area under the graph AB. So it's going to be integration of A dB, right? That's your area. So P versus V, the integration of P dV is your area under the graph. Okay. So part B. What is the change in internal energy of the gas? So it goes to the first law. And changes of U is Q plus W. Q is positive 2000, positive, and W is negative 500. Negative 500. Though this careful, that sign is metal, negative 500. So change in internal energy is 1500. Okay. So any question from this slide? No questions, Okay. Okay, before we go to this, I need to tell you something. Back to the whiteboard. Solid, liquid, gas. Okay. Solid to liquid, changes of U is moving from solid to liquid. Changes of U positive or negative? Anybody? Solid change to liquid. Internal changes of U, increasing or decreasing?
Decreasing.
So positive lah, rises. Liquid to gas, changes of U, rises. Okay, goes up. Okay, goes up. But in your mind, if you use first law, if you use the first law, how do you can change solid to liquid? By either supplying Q or doing work. Okay, you do both. You do this, you can change the changes of U. Okay. Okay. For liquid to gas. Okay, for liquid to gas. Okay. Now the question is, I want to tell the gas, I go to another state. I won't say another state. Another state, it's not another state, it's gas again. Gas. But this gas is the gas 1, gas 2, expansion. Expansion. Gas has been expanded. Expansion. Okay. Expansion. What happened to the changes of U?
Increases.
Increases or decreases? Gas just expanded. And gas expanded.
No change.
Okay.
Negative.
Gas internal energy drops. Negative, right?
Or is it just the same?
Okay, you see, your perfume. You have a perfume. Okay, the perfume. The perfume inside is like perfume is liquid. Okay. Okay. Maybe your fire extinguisher. Okay, you could take a fire extinguisher. Okay, the fire extinguisher inside contains gas, but the gas is in terms of liquid, right?
Yes.
But the gas has been compressed and kept inside, correct?
Yes.
Okay, same thing your perfume the gas has been compressed inside. When you release the gas outside, when the gas comes out, when you touch the gas is cold or hot?
Oh,
Cold. Cold means the internal energy decrease or drops or rise?
increase.
Decrease. So when a gas expands, internal energy decreases because it becomes cooler. Internal energy decreases. In other words, you can use first law. Changes of U equals to Q plus W. Okay, you didn't supply any Q. Heat you never supplied. But the gas expand. Work is positive or negative? Expand. Expand work positive or negative?
Negative.
Negative. So what happened to your internal energy? Negative lah. So the internal energy decreases. Okay, internal energy decreases.
That's if there is no heat added to that gas, right?
Without no adding heat. You never had heat one. When you your perfume, when you press it, you heating it.
No.
You never heating it. So no Q supply lah. Okay. The internal energy of the gas is decreasing. But the point here is when the gas expand. When the gas expand, sorry, changes of view. Yeah, so changes of view become negative. Internal energy become negative. Okay, so that's the idea I want to emphasize here. Changes of view for solid to liquid rises, liquid to gas, its internal energy rises further. And the gas expand, internal energy decreases. Internal energy decreases. Okay. Okay, now solid to liquid, liquid to gas. Yes. Okay. So now I go back to this the PowerPoint, the word file. We talk about evaporation. This question will come back later. You can give a try. Okay, these questions. Okay. We talk about internal energy. So internal energy of a material is what? So you need to write some here. What you can need supposed to write here. Internal energy of a material is the anyone? Is the sum of, guys, come on. What is internal energy? Internal energy is the sum of kinetic plus potential.
Potential energy.
The sum of kinetic plus potential energy. Next line, please write the word. I don't know why it's taking a long time for me to get. The next, second, kinetic energy of the material is dependent on what do you need to write here?
Temperature.
Temperature. Temperature rises, a molecule absorbs, vibrates more. The potential of the materials depends on the separation between the molecules, except, yeah, temperature of the molecules. In the case of melting or boiling, EK does not change. Yeah. During melting boiling, EK does not change, EP changes. Then we talk about first law of thermodynamics. The internal energy of the material is U equals to, write again the formula. What is that? The sum of EK plus EP. Okay. Then number three, when the quantity of heat is applied to fixed mass of gas, its temperature may increase, cause increase in internal energy. Okay, point four, something to fill up. If the gas expand, then there is external work done by the gas. The work is what formula? Right? P changes in volume. Okay, P changes in volume for a constant pressure for a constant pressure. I'm happy to see that you put an integration PdV. Okay, it's a high level of writing. Okay, I think that's the best. But normally A levels, your mark scheme, all they put P changes in volume. This will cause a decrease in internal energy. Yes. When the gas expand, the effect to the internal energy is the internal energy might go down. Okay. So changes of U is Q plus W. Heat transfer into the system, Q is positive. Heat removed from the Q system, like cooling, Q is negative. And next, compress, W positive, expand, negative. Okay, so now your turn. Okay, now I want you to fill up this box here. Thermodynamic law, first law. Please fill up here. If it increasing, put positive. Okay. If it's decreasing, put negative. If no change, put 0. Okay, put 0. Positive, negative, or 0. Okay. Use first law of thermodynamics. Okay, first, expansion of ideal gas at constant temperature. Can you figure out which going to be positive, which going to increase, which going to be decrease, which no change? Okay, I give you 1 minute for you. Try to figure out the, maybe we do the first one. We do the first one. Okay, first one, tell me. Expansion of ideal gas at constant temperature. The first thing you can fill up always is work. Work easy to fill up. Because work, if it expand, compress, if there is a change in volume, work involved. If it expand, work is negative. When it compress, work is positive. You now tell me for the first one, expansion of ideal gas at the constant temperature. Work positive, negative, zero?
Negative.
So work is negative. It's expand. Keep a negative effect. Okay, now Q or changes of U. We don't know if heat has been supplied or not. We are not sure. They never tell heat has been supplied. I think next you can find the internal energy. Tell me internal energy. What do you think? Expansion of ideal gas at constant temperature.
Negative.
Internal energy decreases. Internal energy decreases at constant temperature.
But wouldn't decrease the internal energy would balance out with increase in Q?
Okay, hold on. The first law and also the what is meant by internal energy law? What is internal energy? Changes of what is sum of EK plus EP, right?
Yes.
I right here. I couldn't write on top of it. Okay. Okay, internal energy is what? EK plus EP. EP plus EK. Ideal gas. The question is about ideal gas. Ideal gas, which energy is zero? EP0, EK0. Ideal gas. Ideal gas, EP0, EK0.
Oh.
What is zero?
EP.
EP0. EP don't have, remember, whenever they say ideal gas, it don't have EP. There's no intermolecular force. So you must conclude this internal energy formula as internal energy only for ideal gas. Internal energy of ideal gas only depend to what? EK only. Only for ideal gas. If they say real gas, EP is there. But if they say ideal gas, ignore the EP, no EP. So internal energy for ideal gas is only EK. EK never change. Internal energy never change. Kinetic energy proportional to what? Anyone? Kinetic energy proportional to what? Temperature. Now tell me the answer. The first one. What is the answer?
That means W is 0. Okay, is not changed. Like,
so no change.
So W is no change.
Not about W, the U, right? Internal energy. So expansion of the ideal gas at a constant temperature. EP don't have. EK also, is there any change? Constant temperature. It expand with constant temperature. Is there any temperature change?
No.
No temperature change, right? If temperature never change, EK also never change, right? EK also never change, right? So what happened to the internal energy change? For the first answer here, must be zero. No change in internal energy. Ideal gas, the change in internal energy is zero. Okay, what is internal energy? EK plus EP. But ideal gas, no EP. Because constant temperature, EK also never change. So internal energy never change. No changes in internal energy.
So doesn't that mean that
Yes.
all factors are the same?
All fact again. What's your question?
Since there is no EP, that means work is not changed, not negative. It's just not changed, right?
Why? Gas expanding what? Gas expand, work is negative. No?
Yeah, but there is no potential energy.
Yeah, you don't have potential energy, but by expanding the kinetic energy of the particle, by expanding, what happened? Then yeah, correct. Because expanding means work definitely done. But what is meant by work? What
Oh,
is the work formula? What is work? Cost times distance travel, right? Cost and distance travel is the work, right?
yes,
Correct. Is there force applied and the gas expand?
yes,
How the piston move up? Gas expand means gas pushes the wall, right?
yes,
The force is applied, distance travel. Is there any work?
yes.
The work is got it's not zero, right? It has a value one.
Okay.
In this case, work is negative. Why negative? Because expanding. Expand means negative. Negative. Why negative? Because you give a negative effect to the internal energy. Okay, you got the two values independently. The third one you can find by using the first law. Okay, use first law. Tell me, the heat going to be positive, negative, or zero?
Zero.
What is the first law? Changes of U equals to Q plus W. For this case, internal energy is zero, but work is negative.
Oh, that's positive.
So Q will be positive. Okay. So this law is based on conservation of energy. This always applies for a closed system. So work was negative, no change in internal energy. That means from where you get energy to do work? From heat. You need to apply heat to do work. Okay? You want to do work. You want to run. From where you get energy? Either you eat, you, or you burn your fat. Okay? But in this case, look like the gas never burn its fat. The changes of U is zero. You never take anything from internal energy. But work has been done. So from where you get energy from? You need to supply energy lah, heat Q. So Q in this case is positive. That's the first time should be fitting. Any questions for the first one? So my advice is when you use first law of thermodynamics, the first column always can fill with is the work. Then get the work value first. Is it positive, negative, or zero? Work easily can be discovered. If it expand, work negative. If compress, work positive. If no change in volume, work zero. And next, you need to find out another one of them. Either changes of U or Q, you have to find individually. That's difficult. But normally, they will hint you something. They'll tell you like heated, they'll say it's cool. Then Q, you know. Okay? Or temperature rise, you can find the changes of U. Okay, class. Now I try the second one. Fill the work first for me. Come on. Second one, work is what? Positive, negative, zero. Anybody?
Negative.
Pressure of ideal gas at constant
Right.
volume. The
Right.
work is
Constant volume.
what?
Negative.
Is there work done?
Oh wait, no work done.
Why?
Oh, this
Because constant
constant.
volume. Constant volume indication that no work has been done. So work is zero. Okay. Okay, guys. Next, decrease in pressure of idle gas at constant volume. We are clueless whether heat has been supplied or it has been removed. So Q should be the last to find out lah. So now you need to use internal energy. I think changes of U. How to find changes of U? Tell me. With the temperature of this again idle gas, this again idle gas. So because it's an idle gas, the internal energy only depend to what? Internal energy is only depend to, the U only depend to EK, which is proportional to temperature. So now you have to check decrease in pressure of idle gas. When the pressure of the idle gas decreases, you need to check, is the temperature of the gas dropping or rising? If the temperature, if you can find the temperature is dropping or rising, you can figure out the changes of U already. The temperature drop means changes of U dropping, right? Because it's an idle gas, right? Idle gas. So U proportional to temperature finally, only for idle gas, only for idle gas. So tell me, temperature dropping or rising? Decrease in pressure of idle gas at constant volume. Pressure decreases, constant volume. You have to use your gas law. What happened to pressure? What happened to temperature when pressure dropped? Volume constant. Pressure is dropping. What happened to temperature? But volume is constant. What law you use? How pressure and temperature related? They are proportional or inversely proportional? This is for gas law.
Directly proportional.
Directly proportional. Or you can think about PV equals to nRT like if you want. This also can. Volume never change. Pressure decreases. So what happened to the temperature? Temperature will decrease. Okay. So because NR is constant, it's a closed system, number of mole are constant. So you can predict the changes of U. Changes of U, positive, negative, or zero. Anyone? Temperature decrease. Temperature decrease means internal energy is decrease. So negative. Internal energy is changes in internal energy is negative. Okay, now you got the changes of U. According to first law of thermodynamics, internal energy is dropping. No work has been done, but internal energy is dropping. So Q, the system need to be cooled or need to be heated. How you can reduce the gas pressure? By cooling it or heating it? So Q here, positive or negative? First law?
Positive.
Tell me. Positive. Yeah, positive. Positive. Go to the first law. The first what? Change of U equal to Q plus W. Change of U is negative. Work is zero. So Q must be negative, right?
Yes.
So Q must be negative. So the gas need to be cooled. The gas need to be cooled to reduce the internal energy without doing any work. Okay? Ready? Okay. Next, third one. Okay, third one, I need to add something here. Free expansion. Free expansion means act of nature. gas just allowed to expand by itself. That means what quantity is zero? The gas just allowed to expand by itself. What quantity is zero?
Intermolecular and internal force, internal energy.
Internal energy zero. Like like your perfume, you open the valve, the gas expand freely. You just expand. The gas come out, it just expand freely by act of nature. Is it getting cooler, right? Internal energy change or not? Internal energy changing, right? Because the liquid the gas comes out is getting cooler compared to the inside. Inside the container is room temperature. When you press the valve, it comes out, it's cooler. It means internal energy change or not? Internal energy changing, right? Because temperature change. Right? Free expansion means the Q zero. No heat supplied or removed. You never give heat, you never cool it. Q is done by human. Human. You heat it or you cool it by freezer. If free means you never apply any heat. Never apply heat or never remove the heat. Okay, so Q is zero. Okay, remember, very important. When they say free compression or free expansion, Q is zero. When they say changes in volume is zero, means work is zero. Okay, and they say no change in temperature, means changes in internal energy is zero. Please remember this, put it into your notes. Free compression expansion, heat zero. No changes in volume, work done zero. No changes in temperature, changes in internal energy zero. Okay. Okay, now please fill up the free expansion of ideal gas. Anyone? Next, what you can fill? Work. Work going to be what?
Increase.
Yeah?
Wait.
Negative, positive?
Then.
Negative. Why? It's expanding. Negative. Expansion. Expand work is negative. So based on first law, how much changes of U will be? What is the changes of U will be?
Negative.
Positive, negative, zero?
Negative.
Negative. Yeah. What is negative? Okay, so I never expect all of you to get this for the first round. Okay, all the classes like that. But if you manage to get the third line, good. Okay. So this is how the first law of thermodynamics is used. Okay, first law of thermodynamics used to find the third quantity. First law of thermodynamics is normally used to find the third quantity after you know the other two. Okay, the other two you need to find individually. Most of the time, work you can find individually. Another one you can find individually is sometimes changes of U, sometimes Q. Okay, you see when they say free expansion, we definitely know Q is zero. We know Q already. Sometimes they never tell heat supplied or removed. Then you don't know the Q. You need to find the U, changes of U. Changes of U. Okay, constant temperature means changes of U know already. Zero. If like second case, a little tricky. Pressure is decreasing with constant volume. Then you have to use your gas law. You have to use gas law to find that. Okay. Let me tell you. For P versus V graph, this law sometimes they give expansion of gas law. Let's say a gas moving, going up like this, going to this point, and coming back here. Okay, gas. point A, point B, point C. The closed system. Okay. Tell me, point A or point B, the temperature, the internal energy is higher. Internal energy at A higher or internal energy at B higher? Use your gas law. You can use PV equals to nRT to adopt this. Anyone tell me? Internal energy at A, internal energy of the gas at A higher or at B higher? The gas move from A to B. Anyone with a reason? Which point most likely the internal energy is higher?
B.
B. Good. B is higher than A. Why?
Temperature increase. B increase,
How you know?
temperature increase.
Why you say temperature increase?
Because the pressure increase, but the volume stays constant.
Yeah, because in other words, the product of PV is greater. The product of PV is greater. Here, the A PV value is this P and this V, small number. B is big P, small v. So the product of PV and B is bigger. So PV bigger means temperature will be higher, mathematically, right? B higher or C higher? Internal energy of B higher or C higher? Internal energy B higher or C higher? Anyone? Which higher? You can use your gas law.
B
equals to
higher.
NRT. Yeah.
B higher.
B higher. B you see PV here. C you see P times V here. Which PV value greater? The product of PV of B greater or product of PV of C greater?
Oh.
C gets a greater PV, right?
Yeah.
So C. So temperature of C is higher, right?
Yes.
So internal energy of C is greater than B.
But wouldn't increase in volume also decrease the work?
Yeah. You use the law also. You get to know, you use changes of U equals to Q plus W, right? Of course W become negative, right? But changes of U you will get positive because your Q will be more positive.
More positive.
If you use the law, you will find out the Q will be more positive. So your changes of U will definitely rise. Use U equals to changes of EK plus EP. You found U is positive. Using the second law, the first law also, the changes of U, you will get positive. Okay. Okay. So if they give PV graph, you roughly get to know changes of U rising or not. And the point is further away like this, further away where the PV value is bigger. So by using the gas laws, PV equals nRT, temperature also must be high. So it should have a higher internal energy compared to the lower one. Okay. Can you see the question here, number 7? Tell me, PQRS, at which point the gas has the greatest internal energy? At which point the gas has the greatest internal energy? Anyone? Sorry, hold on. Yeah. Can I move that? Hey guys, so which point? PV graph. The gas change like this. Okay, this is the first state P, this Q, this is R, this S. The UP greater, UQ greater, US greater, or UR greater? Which potential energy, internal energy is the highest? Anyone? This gas law. Gas law is what? PV equals to nRT. Which has the greatest product of PV value?
R.
R. So R has the greater internal energy among the other 3 points. R gas attained the greatest internal energy for sure. Why? Because the temperature is the highest among the other state. Which has the lowest internal energy? Which has the lowest internal energy?
P.
P. P has the lowest internal energy. So EP. So if a gas moves from P to R, for sure you can predict that the changes of U going to be positive or negative. P to R. P to R, internal energy rises, right? UP roll, UR. So changes of U must be positive. So this is how you predict the changes of U, from the graph, PV graph. More further the point, U is getting higher and higher. If any point lower go to R, changes of U definitely is bigger, positive. So in the box, just now, changes of U, Q plus W, you can predict changes of U already, it's going to be positive. You go from P to R, I'm telling you. Okay. And work, you can see P to R. If you go P to R, work is positive or negative. P to R. You expand or you compress? Anyone? P to R. Your volume you increase, right? You see your x-axis volume. Volume increase, so work going to be positive or negative. You expand, so it's going to be negative now. So from here you can predict the third one by using the first law. Changes of U positive, work is negative, so Q must be positive or negative. Must be a big positive. Okay, so this is how you predict the third one. Okay, students. So this is the new idea. First law of thermodynamics is the something added in this topic, something new, something important. Okay, very useful in engineering, especially for automobile, to design the engine so that to improve the efficiency. Okay, the first law of thermodynamics is based on conservation of energy. Okay, scientists by heart they are trying their best, the engineers trying their best to make all the heat supply to convert it to work done. Okay, try to minimize the internal energy change. Okay, so that's the idea. Then in physics, we're going to talk about how the internal energy changes. So changes of U, changes of V. If volume doesn't change, what zero? Work is zero. When they say free expansion or free compression, what is zero? Q zero. Okay. When they say constant temperature for ideal gas, what zero? Changes of U zero. Okay. Okay. So my advice before the next class, go to the PowerPoint, look at these questions, the solutions. There are few questions you can give a try. Okay. Go to the Word file. Go to the Word file here at the back. There are plenty of questions. Towards the end, you have the thermodynamic questions. Question like degree Celsius. Yeah, the 13, question 13. You can think about the thermodynamic. You can give a try. Okay, so homework. Try example 8. Sorry, not example 8. Try to do the example 7 as a homework. Okay, the idea I told you. You get the answer good. If you can do example 8, I'm quite happy. Example 8 is filling up this table. Okay, quite happy. I'll give a try. Tomorrow we'll be discussing these two. Any questions, guys, before we stop? So what did you learn today? You learn about evaporation. You learn about internal energy. You learn about first law of thermodynamics. Most of it something new. Internal energy and thermodynamics. Okay. Any questions? For no questions, I stop here. Okay, see you. Bye.